Everybody. So good morning, everybody. It is my very great pleasure and honor as well to welcome Reinhard Genzel at IAP, unfortunately virtually, for today's colloquium, where he will describe a 40-year journey that brought him and his colleagues closer and closer towards the single massive black hole at the center of our Milky Way. Reinhard's career started in Bonn in the late 70s, I think, at the Max-Planck-Institut for Radioastronomie, where he wrote his thesis under the supervision of Peter Metzger. And subsequently, he went to Harvard and then Berkeley University, initiating the many remarkable journeys that he undertook in science. All these journeys are intrinsically linked to supporting pioneering developments of very sensitive instruments, mostly in the infrared and the sub-millimeter, millimeter, to explore mostly the structure and activity of galaxies near and far. And each time along these journeys, Reinhard's aim was to increase the capabilities of the instruments, aiming to study galaxies at higher angular resolution and at greater distances as well. The facilities include the ESO telescopes, such as the VLT, Herschel, some time ago, the Kerr Airborne Observatory, or of course, the IRAM NOEMA interferometer, just to name a few. And in doing so, Reinhard built and trained generations of astronomers and engineers, creating a long-lasting legacy as well. Reinhard is director of the Max-Planck-Institut for Extraterrestrische Physics in Munich, and also a full professor of physics at the University of California, Berkeley. And he is member of many prestigious institutions, including the French Academy of Science. His many scientific achievements and discovery have been recognized by many awards, from the Otto Hahn Medal to the Tycho Brahe Prize, and most recently, as you all know, he received the Nobel Prize for Physics 2020, together with Roger Penrose and Andrea Ghez, honoring their research on black holes. So after this brief introduction, where I left many things aside, there's so much to tell about Reinhard that, again, I would like to welcome you, Reinhard, and I will give you the floor, or rather, I would say the screens here, to report on your 40 years journey towards the center of our galaxy. So, Reinhard, it's all yours.
Well, thank you, Pierre. Dear colleagues, dear friends, I would have liked to be there where you are, so we could have seen each other in 3D. It's hard to believe that we are three-dimensional individuals after 1.5 years of this digital world. But so be it, at least for now. Yeah, my talk I've named a 40-year journey. You will see why. What it is, what we've tried to do here, is to test general relativity in a general sense as a physics experiment, but at the same time, the massive black hole paradigm with one object, namely the nearest galaxy, the center of our own Milky Way. And as you will see, we had to take a number of steps. And as Pierre already indicated, these steps brought us forward as we were improving instrumentation and so forth. And I'll try to emphasize, how that went. Now, of course, this kind of a long journey takes time as well as energy, and you have to have friends, many friends, to walk with you and work with you. And so I want to absolutely recognize the many people who have been part of this endeavor, including many people in Paris and also Grenoble. And then, of course, also at the European Southern Observatory, both in Garching as well as in Chile. So really, this is a wonderful European collaboration over a long period of time, where I think we've shown what we can do together as a team, doing a difficult thing. Of course, as I mentioned, instrumentation plays a key role. When we started, infrared work was still very difficult because, you know, one had one detector, typically a bolometer, and was basically scanning the skies to get pictures. And of course, we were limited by the seeing of telescopes in the near infrared to you know, fraction or an entire arc second. So that was very poor. But over time, we learned how to overcome that. Initially through speckle observations, then using adaptive optics, moving on to the Very Large Telescope with NACO, then introducing field spectroscopy plus adaptive optics with Symphony, then introducing laser guide stars, and then lately, as I will come back to, in fact, combining the entire 4 8-meter telescopes of ESO in an interferometric way, which was a tremendous challenge to do that experimentally. So that is really a long path, and the motivation for this path is obvious. We know since 100 years that Einstein's theory predicts black holes. Martin Schwarzschild found the first solution of a spherically symmetric system, and because photons see gravity as well, all of a sudden you have a new feature, which is an event horizon, where if an object is smaller than this event horizon, given a certain mass, well then things inside the event horizon cannot communicate with things outside. Now, this picture was then refined over the years. Roy Kerr showed that there's a second property a black hole can have other than mass, which is spin. Charge is another one. But it wasn't clear really altogether whether these high spherically symmetric analytic solutions might not just be very special cases, and in a general case, black holes might just be a mathematical construct. That's the role of Roger Penrose, who I shared the Nobel Prize with, and Andrea Ghez last year. And Roger really is a remarkable mathematician who managed to use topology to show that, you know, starting, given a minimum curvature of space-time, a black hole ending, so to speak, is unavoidable. Now, of course, as you all know, this is all a classical theory, and we all suspect that on small scales, there must still be extensions of the theory which have not yet been done. Stephen Hawking, of course, has told us that Heisenberg's uncertainty principle makes it very likely that there's radiation escaping from the event horizon, although practically we cannot detect that in astronomical objects. But I mean, there is a tremendous future here to go and explore these objects. But of course, the critical question is, do they exist? And it took 50 years before the discovery of bright neutron star binaries or black hole binaries in X-ray astronomy on the one hand, and then discovery of quasars by the radio astronomy community really paved the way to put this search for black holes into the center, to the focus of many of us. As you well know, when discovering the quasars and then seeing how far they were away from Martin Schmidt's work on Palomar, a number of theorists, including Donald Lindenbell, Martin Rees, Rashid Sunyaev, Roger Blandford, and many, many others, immediately proposed within about a decade that the most likely explanation for the very large luminosities of quasars, up to 100,000 times the luminosity of the Milky Way within a volume of only maybe a light year or so, could be due to a massive black hole accreting a lot of material. And the material, as it spirals inward, removes angular momentum, spirals inward in a perhaps disk-like configuration, and before disappearing within the event horizon, would then basically convert its gravitational energy, its potential energy, into thermal energy and radiation. And that could indeed explain an enormous amount of energy output, up to about 40% mc squared for an infalling proton. At the same time, of course, quasars, when they were discovered, also showed up as sources of energetic radiation, X-rays, gamma rays, and of spectacular collimated radio jets. But of course, this is not a proof that these objects really truly are black holes. For that, Lindenbell and Rees proposed one must actually use, if you like, Kepler's technique of using a central object and the surrounding objects and testing the distribution of the gravitation potential by the motions of these test particles. Now, this idea, of course, came in the early 70s, and by the mid-70s, as I will explain to you, the first experiments, observational attempts were made to do this, although not in quasars, because they are far too far away to resolve them with techniques available then. We could do that now, but not then. And so this is where, of course, it's critical to have the possibility of go to closer objects. And Lindenbell and Rees, in their 1971 paper, proposed that perhaps galaxies other than distant quasars might have such black holes, including our own. So that's sort of the beginning of the story. And so then it took a number of years, and now we are in the situation that in the galactic center, we have what is a very convincing set of pieces of evidence that, number one, the theory of general relativity indeed applies surrounding the central radio source, Sagittarius A star, and that Sagittarius A star indeed is a million solar mass black hole beyond any reasonable doubt. The second tremendous breakthrough a few years ago, of course, as you well know, is the detection of gravitational waves from inspiraling and merging stellar black holes, with now about 55 such objects seen by LIGO, and really providing a rather spectacular confirmation of Einstein's theory right next to the event horizon of such objects, and making it very, very likely that these objects indeed are Schwarzschild Kerr black holes. Finally, the radio astronomy community has been successfully using very short wavelengths, very long baseline interferometry to look at the center of the nearest very massive black hole in Virgo, M87, and gave us in 2019 this beautiful picture where you could see definitely the effects of gravity on the photons in the central region, and plausibly consistent with the photon orbit predicted by general relativity. We are hoping to see pretty soon the combination of the radio method and what we are doing in the galactic center. And indeed, it may very well be that later this year, our colleagues from the Event Horizon community will publish a paper on the galactic center. We'll see what that gives us. So within, a period of 20 years or so, after 100 years of theoretical work, we are, for the first time, doing physics and testing this theory. As I mentioned, initially, Lindenbell and Rees were the ones to propose to go and look at the galactic center. Now there's a problem which you see immediately when we fly in from the outer parts to the 27,000 light years away center of the Milky Way. Namely, there is dust between the stars, very thick dust, which obscures optical wavelengths so that you cannot look at the galactic center in the optical. You can do so in the infrared, you can do so in the radio or X-rays, but not in the optical. And so we needed to obviously develop techniques to image radiation well with low, with high sensitivity and low noise detectors, and get sharp images. And as I told you, this has a lot to do with instrumentation development in the 1970s and 80s, in part benefiting from the American military and their interest in imaging Russian rockets, and thereby developing imaging semiconductor detector arrays, but also adaptive optics, which while it was also done in the military domain in the US and later declassified in Europe, especially in France, actually led to early developments at ESO for a civilian development of making sharp images. What you see here is a modern VLT image at 3 infrared colors of the central few light years in the galactic center. And you see the spectacular concentration of stars, some of them blue. Eric Beckland and Gary Neugebauer, who for the first time made images in the galactic center, already had detected these stars, and clearly much more massive and luminous than the sun. So these are objects between 50 and 100 solar masses and ages of a few million years only. And then there are the irregular objects, which are giants and supergiants. So it's a very spectacular region. Actually, Martin Rees, who, as I just mentioned, in 71 had said, look at the galactic center because there might very well be a black hole. When he saw images of that type and also the spectrum showing definitely that there are young stars, actually then said there is no black hole because star formation in the vicinity of a black hole is very likely to be prohibited because of the tidal forces of the black hole. Yet here we are and have one of the most spectacular star forming regions in the entire Milky Way. Now, the radio astronomers also have been looking at this region. And finally, the infrared community has been looking at the gas in this region. There's ionized gas, which you see here in pink color, and neutral gas, the green color, centered on the stellar cluster, which you see in blue on the same kind of a scale. And then in the center of all of this is a very compact radio source, Sagittarius A star, which we now know has a diameter of less than about 40 microarc seconds. So that's about 20 centimeters on the moon, and only a few times the event horizon size of a few million solar mass black hole. So there, X marks the spot, you would say. That is our likely candidate. And we now would like to use the technique of dynamics to test out the gravitational potential. Now, Charlie Townes, Nobel laureate for the invention of the laser and the maser, had moved by the end of the 60s from MIT to Berkeley and started a new career now as an experimental astrophysicist, developing novel instrumentation, spectrometers with his students and postdocs. I then became one of these postdocs initially, and we looked at the galactic center in some detail, mapping out the distribution of the Doppler motions through spectroscopy of infrared lines, in particular the neon 2 line at 12.8 microns, but also the green in oxygen 1 at 63 microns from the Kuiper Airborne Observatory. And then we were able to map out the mass distribution as a function of distance from Sagittarius star. That's shown on the left side. And if you go from the outside in, you see that initially the mass drops. Well, that's clearly the indication of an extended mass. So that's just the nuclear star cluster. But then inside of about a parsec, about 25 arc seconds in the galactic center, the mass does not change much anymore and stays nearly constant at around 2 to 4 million solar masses. So in 1985, he published a Nature paper saying, well, there it is. That's a black hole at the center of our galaxy. Well, is it? Well, many people were skeptical because, first of all, the gas we were using is, exposed to forces other than gravity. The ionized gas, in particular, can be pushed around by magnetic fields, and it was very clear that strong magnetic fields were present in this inner region. Second, there are stellar winds from these massive stars. They also can push the gas around. So the gas is not an ideal tracer of gravity. And second, while we were proudly making measurements at a few arc-second scale from Sagittarius star, that's 1 million times the event horizon of a 4 million solar mass black hole. So most people felt good work, but you have to do better than that. And so I then moved from Berkeley to here to Munich, formed a new group, and we started building new instruments. We used these techniques of novel detectors and detectors which were good enough, in fact, that coupled with a new telescope the ESO had on La Silla, could take pictures in short exposures, which gave us the diffraction limit of this new technology telescope, about 1/10 of an arc-second resolution, so about 5 to 6 times better than in seeing limited imaging. And so we went ahead and took these pictures from year to year. At the same time, or a little later, Andrea Ghez and her colleagues, Mark Morris, Eric Beckton, and others, used a new Keck telescope, 10 meter in diameter, and started the same kind of a measurement. And after a few years, both groups did have good evidence for a mass concentration, which in fact you can see in this picture, which are superposed images, high resolution images at 3 different years in red, in green and blue. And you can see that near Sagittarius star, which is that cross, there are stars which clearly change position from year to year and have a velocity of 1,000 to 2,000 kilometers per second. So if you do b squared times r over g in a first estimate of the mass, you get a few million solar masses. So that's the same mass we had with the gas 10 years earlier, but now with a better tracer, and actually also on a smaller scale, about 100,000 times the event horizon size. That green circle there is 1 light month. So we are now on a scale of less than a few light weeks. And clearly the mass is concentrated because when you go out from the center, the images of the stars become wider and wider, which indicates that their motion is smaller and smaller. Well, that's Kepler's laws right there. So statistically, both groups found the same thing by 96, 97, 98, that there's a few million solar masses within about 100,000 times the event horizon size. So people were, more willing to accept that as a first indication, but still not good enough to exclude other configurations. For instance, you could think of a cluster of neutron stars or other faint stars inside this region looking like a black hole, but not being one. So what do we have to do better? Well, higher resolution and hoping that you could, over time, get away from the statistical measurement of motions to an individual measurement of motions from individual orbits. Now that is a tall order, because the orbital timescales for most of the stars here are hundreds and even thousands of years. So that's longer even than the lifetime of a Max-Planck director. So clearly, we had to hope that nature would help and give us stars which are very close. Fortunately, I should say, as a side remark, we didn't have to go to do the research to a peer review, because I'm sure we would have failed to get any money, because very clear it's completely excluded from normal gravitational relaxation mechanisms to expect to see what are relatively young stars. These are B stars of ages of tens of millions of years, to find them so close to the black hole, because the relaxation time of this cluster is a few billions of years. So, you know, you can expect stellar black holes and faint stars, but not massive stars. So anyhow, we did go ahead, and nature was really gracious. It gave us this star, S2, or our colleagues at UCLA call it S02, which is on a highly elliptical orbit, as you see, and came around the corner, if you like, and at a peri of only 17 light hours in 2002. By that time, we had already moved to the VLT, and together with our colleagues in Paris, had put on the telescope a adaptive optics imager, NACO, combination of NEOS and Konica, to exploit the full resolution of an 8-meter telescope. So another factor of about 3 or 4 better than what we had before. And so we could really map out the motion. And now if you measure the velocity near peri, you go up to about 2.5% the speed of light. And again, v squared r over g at 17 light hours, which is 4 times the Neptune orbital radius, gives you 4 million solar masses. So the same 4 million solar masses which we had seen all along, but now within only about 1,000 times the event horizon size. Now the theorists had a hard time finding any kind of alternative configuration which would fit in there. The dark horse was a so-called boson star, which nobody had seen before, but might in principle fit in there, yet be unstable to baryonic accretion. So that looked very, very promising. And as you see, the scientific principle was also upheld in the sense that the blue measurements from Chile and ESO and the red measurements from Mauna Kea, tell you the same story, really the same story, to within 10% or 20% or so. Okay, so that looked pretty good. Most people were convinced. Certainly the astronomers were convinced. But in order to conclude really that this is that any other configuration is unlikely, we do have to assume now general relativity in any kind of a consideration of stability of alternatives, etc. Now the star has a lifetime, an orbital time of 16 years. So we knew, and Andrea knew, it'll come back in 2018. And we thought hard what we could do to be ready by 2018 to then, in fact, test general relativity and turn the galactic center into a physics laboratory. And the answer was, as you will see in a second, interferometry. But in the meantime, of course, we were enjoying, if you like, the enormous complexity of the stellar configuration and motions in the center, which we got with the adaptive optics imagery, including spectroscopy. Fact that these innermost stars are on highly elliptical orbits, which are completely randomly distributed, very surprisingly, and then surrounded by what looks like a thick disk of O stars and Wolf-Rayet stars. We now think that the Owen Wolf-Rayet stars actually formed from a disk of gas, which fell in, cooled down, and then finally became gravitationally unstable, while the innermost B stars, the so-called S stars, are probably remnants of binary stars, which are on near lost cone orbits, moving into the center, getting accelerated, and then into the three-body collision with the big black hole getting unbound, so that one star gets ejected into the outer galaxy and beyond, while the other one gets stuck near the big black hole. This is the so-called Hill's mechanism, which is the most likely explanation for this configuration. All right, so let me go to the next step, but remind you that we were building on the shoulders of giants. The VLT has 4 8-meter telescopes. Actually, as you may recall, the plan had been to build one 16-meter telescope, but that was technically not possible when the plans were made by Lo Volcher and his team and the council in the 70s. But a number of people, in particular Pierre Lénard, but also Jean-Marie Mariotti, Fritz Merkle, Tarangi, and Gerd Weigel and others, convinced ESO that a distributed array of 8-meter telescopes could eventually be used for interferometry, which for radio astronomers, of course, is obvious, but for optical astronomers is something which you would say is possible in theory, but unlikely in practical terms because of the short wavelengths, the short coherence time of the atmosphere of only a milliseconds, and all these difficulties like vibrations and measuring distances to nanometer scales, et cetera, et cetera. But, and that is what I want to emphasize here, Pierre and others did convince in the end ESO and the council that one should build the 4-meter telescopes, the 4 8-meter telescopes in a way which was optimized for interferometry. So not in a line actually, but slightly offset in north-south direction so that you get a bit of a north-south baseline as well. So that was sort of a reminder that we, when we started to think about the next step, we could build up on this already existing machine and now build a beam combiner in modern terms, which could optimize the effective resolution of this 4-meter telescope interferometer of a maximum baseline of 200 meters and giving us the option of a resolution jump by another factor of 20 over that of 8-meter telescopes. So this experiment was led by Frank Eisenhower at our institute, and as you see, a number of European institutions, the Observatoire de Paris, of course, Observatoire Grenoble, Max-Planck-Institut for Astronomy in Heidelberg, University of Cologne, and the Lisbon Porto Observatory, together with ESO, worked for 10 years to realize this machine gravity, which most people thought wouldn't work because of the difficulties I mentioned, and certainly not be sensitive enough to look at the galactic center. Charles Towns, in fact, was one of the first people who also pushed forward in interferometry, but basically never managed to make it sensitive enough to look at the stars in the galactic center, although he dearly wanted to do that. Interferometry up to gravity could look at bright stars, but the stars in the galactic center, and in particular near Sagittarius star, are orders of magnitude too faint. So you have to do much better. And the answer, we felt, is low noise detectors, new generation of low noise detectors, effective beam combination, beam control, and phase referenced interferometry. So the idea is that you track your fringes on a nearby bright star in the field, and then observe at the same time the science object once you compensated for the differential delay line differences the Earth atmosphere has done to you. So we made a little movie of this instrument, which I want to show you now, which we call the last millisecond of the tortured photon. And you'll see why we did so. So here's the beam of light coming from the galactic center, hitting UT1, primary, secondary, tertiary. And now we have to go down into the basement, so to speak, in order to do adaptive optics. The wavefronts have to be flattened for all the 4 8-meter telescopes, because otherwise, of course, we are wasting the big telescopes. And that's done here at the bottom here, flattened wavefronts. So now we can compensate for the geometric pathings to delay in this tunnel system down there, and then bring the beams of the four telescopes together in a laboratory where we have gravity. So gravity is a cryogenic door, so that no more thermal noise is added, and you have no vibrations which affect the radiation. After some additional beam forming, adjustment, correction, and so forth, then you get into the part which I already described to you, where you split the beam here in this prism into 2, one from the star you use for fringe tracking, and one from the science object. Now, in the past, these kinds of beam combiners were out on a big optical table. Here we decided to go into monomode fibers, given the great experience the Paris group had done with that, Guy Perrin and his colleagues. So here we are in single mode fibers, which allow us to do the differential delay compensation, as you see in these coils of single mode fibers, and also control the polarization state of the radiation by being able to twist the fibers. So after all of this, now we have 4 beams which are corrected, etc. Another 4 beams for the fringe track star. So in total 8. And now we go into basically a beam combination system, which is a fused silica device developed at Grenoble, borrowed from communication industry, which then combines all the 4 telescopes into 6 baselines, sample 4 times the different phases, and finally disperse the light so you get spectra. So it's a fairly complicated system. At the same time, of course, we send beams back from the instrument all the way through the telescope to measure all distances within the telescope to 10 to 30 nanometer precision, so that you really are phase stable. And gravity does have sharp eyes. When you do this combination, you can, with gravity, resolve a euro cent coin on the moon. So that's 10 micro arcseconds approximately. So looking over these 40 years of development, we started, as I explained, in the late 1980s, early 1990s, with the first imaging infrared detectors. We could see the star cluster. The radio astronomers could pinpoint Sergei star there. Then we started going to the entity in the fields. We introduced adaptive optics, which allowed us to resolve the central region into many, many stars, which over time moved and gave us these orbits, which I showed. Now, if you look at Sergei star in here, in the central region, that central region now we can actually then resolve with gravity. Now, in 2018, as I mentioned, the star came back, and you'll see the results in a second. But in a way, we thought, okay, we are now actually done for a while, but not so. What you see in the bottom is an image we took this year. And wow, not one, but 4 stars are zipping around Sagittarius star. The star S29 there, in fact, is moving with a velocity of almost 9,000 kilometers per second, and is even deeper in the potential than S2. So that's the fantastic trick here. We have the option to see the motion of these stars from night to night, from month to month, and get very precise information on the 3-dimensional structure of the orbits. And then we can fit for the mass and the mass distribution, the distance to the galactic center at sub% accuracy, along with reference 0 points, etc., etc. So that's the status now. And if you look, what we now know is really, we know the gravitational potential on the scale of about 100 AU, 100 times the distance between the sun and the Earth, very, very well. And in fact, as a function of distance. So we can look for extended mass as well as the value of the central mass, and we can look for effects of general relativity. So there is the Perry of 2018, which I mentioned, which was on the 19th of May of 2018. And you can see these red points from different days before and after Perry. Now, the first effect we hope to see is the gravitational redshift. So when photons are emitted in a spectral line near a big mass, because in a deep gravitational potential, the clocks are going slower, then the line is redshifted. So we can measure the redshift of this spectral line. And of course, you start off with the Newtonian overall result, which you see there on the right, where Perry in 2018 was near the peak there at plus 4,000 kilometers per second. And then you subtract out the best fitting Newtonian orbit to look at the residuals. So now the Newtonian orbit is the gray horizontal line. And what general relativity would predict for this situation is the red line. And the data are the cyan data points. So you clearly see, we confirm the gravitational redshift by general relativity with a very high significance, about 30 sigma. Our colleagues from UCLA also saw the same effect and published a year later. So it's very clear that, again, the scientific principle has been upheld. Now, the next effect to look for is the effect of the precession of the orbit. As you know, in general relativity, if you have a central mass and then the orbiting second mass, then the orbit is not stationary in space, but there is a prograde precession, which in the case of S2 is 12 arc-minutes per orbit. And so that's a challenging measurement, but indeed we were able to do this. On the right side there, you see these two pictures. Again, what we've done here is to subtract in the bottom right, we have subtracted the best fitting Newtonian orbit, and the prediction of general relativity again is in red. So because the orbit is so elliptical and the precession strongly dependent on radius, you wouldn't expect to see much near Apo, where the red data points are. And then near Perry, all of a sudden, the orbit basically exhibits a kink, if you like, and it goes in a different direction, which is indeed the Schwarzschild precession. You see how well the data points follow general relativity. Now, S2 is, of course, now 3 years out of Perry, and so now we can almost at Apo, if you like. So now we can see the precession also directly on the sky. in the upper right picture. So you see the data points from this year are the dark blue circles, and the ones 16 years ago are the open circles. And you can see that the separation is exactly the 0.6 milliarc seconds, which general relativity would predict. But now, of course, we are still out here on a scale of about 1,000 Schwarzschild radii, not yet in the fully relativistic region around the black hole. So we would like to, of course, go into the central region and make some measurements there. And indeed, the galactic center infrared emission is highly variable. It varies on scales of a few hours and sometimes exhibiting strong flaring by factors up to 100. And in such states, one can pinpoint the location of the brightest emission to 20 microarc seconds or so, and then follow the location of the radiation centroid with time. And in the upper left, you see on one of these flares, it started off at this red point, and then within 40 minutes, it did sort of a clockwise loop at a velocity of about 0.3 c at scales of about 10 times the event horizon size of a 4 million solar mass black hole. We have 3 such measurements, which are consistent with the coordinate speed, if you like, of a circular motion around a black hole. Because of COVID, unfortunately, we couldn't make measurements in 2020, and we are still working on the 21 data, but we are hoping in the next years to get more precise information here. Meanwhile, the radio astronomers, of course, as I mentioned, with the event horizon telescopes, are trying to resolve this inner region. The 1 millimeter data are not yet public, but the 3 millimeter data are and show a very compact source, as you see, pretty circular. So there is no indication for a strong jet, for instance, in this region. And that's consistent with the compact structure we are seeing in the infrared. So after 40 years, let's summarize. We've learned that we could go inward from the first indications at about 1 million times the event horizon size of a few million solar mass central object, move inward, showing that the same mass is included as far as every time we went inwards, made more precise measurements, etc., all the way to now a few times the event horizon size. So this is definitely consistent with a black hole. We still would like to measure the spin. We haven't done that yet. For that, we need a star which is still further in. Remarkably so, the measurements are now so good that we can measure the mass distribution as a function of radius in this innermost region and show, and that's shown in the dashed blue line, limits on any extended mass. And you see, these are a small fraction of the total mass, less than 0.1% of the mass inside of the S2 orbit can be an extended mass. So that excludes that, for instance, there's a second big black hole, like an intermediate mass black hole, or, as proposed by some theoreticians, a large concentration of dark matter. When you go further out, then at about 10 times the upper distance of S2, the blue dashed curve meets this reddish curve, which is the prediction of the mass distribution of stars. So that's where, basically the mass distribution is beginning to be affected by the stars themselves, not just the big black hole. But this is really, or appears to be, an isolated black hole. The precision of these measurements is really rather spectacular, as I mentioned, about 0.1 to 0.3% in terms of mass or distance to the galactic center. We've measured the gravitational redshift, the Schwarzschild precession. We can also check the equivalence principle by looking at the hydrogen and helium lines, which are different clocks, if you like, and show that the local position invariance is upheld in the case of the galactic center. And then finally, these flares tell us that the mass is likely indeed contained within a few times the event horizon size of the central region, and there is no evidence for any big other mass greater than about 1,000 solar masses. Are we done? Well, actually, we are not done, because you would like to, if possible, measure the spin, and then in the end, even more importantly, test the so-called no-hair theorem, namely the prediction by general relativity that by having the spin and the mass, all other properties of the black hole are known. Okay, the quadrupole moment, for instance, can be computed from these two numbers, which isn't different from other gravitational theories. So we are working currently in the Gravity Consortium with ESO on an expansion of gravity, hopefully improving the sensitivity by another factor of 100, allowing us also to measure black hole masses all the way up to redshift 2. This project called Gravity Plus is now the highest priority project of ESO until the ELT comes into operation. The Event Horizon Telescope is of course trying to look at the galactic center and mapping it, and we will see how fast they can come to a new result. We and others are working in a European consortium on the first light instrument, Mikado, for the ELT, which hopefully comes into operation in 2027. Mikado doesn't have as good a resolution spatially, of course, as gravity, but it's much, much more sensitive. And therefore, we can get superbly precise high-resolution spectroscopy of the orbiting stars, and thereby easily measure spin and probably test the no-hair theorem. And then finally, in 15 to 20 years, ESA will hopefully launch LISA, satellite complex of 3 satellites spaced by 2 million kilometers, allowing to measure the small vibrations on a relatively low frequency gravitational waves, which would then allow, for instance, to follow an extreme mass ratio in spiral of a stellar black hole into a big black hole, which would be the ultimate measurement in the field. So the future is really bright. Lots of exciting measurements on general relativity are coming up, and the issue of merging of black holes, binary black holes, measuring black hole masses across cosmic time. And finally, of course, what were the first black holes? How massive were they, and how did they grow? Now, of course, this is largely going to be after my time, and the younger ones amongst you hopefully will take over and bring this to new heights. Thank you very much for your attention.
Well, thank you so much, Reinhard, for this wonderful description of your 40 years journey, including the journey of a tortured photon coming from the galactic center. And it's really fascinating. And I think it's also wonderful to see the bright future that is ahead of us with new instruments, more sensitive, etc. So looking forward for new results. So I think the floor is open for questions, and please raise your hand. I don't see. So Marta.
Hello. So first, it's really always fantastic to see that the new things that we keep on discovering around Sagittarius A star. And if I have a couple of questions, but I will start with one. So about S29, the new star, which was, so can you tell us something about, well, first, besides spatial angular resolution, also the sensitivity played a role in discovering it. Since, I mean, I'm not very good at magnitudes, but I think it's a bit faint compared to previous ones. And also, if you can tell us something about what we can learn from S29 that we haven't learned yet.
Okay, well, Martha, indeed, as I said, what's happening there is in a way came as a great surprise, because indeed S2 has a magnitude of 14th magnitude. Okay, so that's relatively easy to see. Yet, just to be sure that everyone understands, the faintest objects before gravity came into operation, you could do interferometry on was 10th magnitude. 4 magnitudes is almost a factor of 100. But the stars we are now doing interferometry on are almost 20th magnitude, almost 20th magnitude. So that's almost a factor of 10 to the 4 times fainter than this previous limit. And S29 is sort of in the middle, about 18th magnitude. And what we're doing right now, I should say, is to combine the different stars we now can see into a common fit. So that has allowed us to improve the significance of the Schwarzschild procession in a year by about a factor of 2. And also, and that's perhaps even more importantly, to really set a strong limit on any extended mass, as I described. Okay, and so this is going to be, in my view, one of the key battlegrounds of the next time, measuring the spin, then perhaps no hair theorem, and then of course explore in quantitative detail what could be located around the big black hole.
Thank you.
Thank you, Reinhard. I think Brigitte, you raised your hand.
Yes. You hear me? Do you hear me? Sorry, no noise here.
Brigitte, you're in 14 dimensions.
I stopped. Thank you, Reinhard.
So, okay, perhaps you should write your question and then I will read it. Gary, you have a question?
Okay, thank you, Reinhard. That was fantastic. And I've always enjoyed listening to you, and congratulations for this amazing journey. So I have 2 questions. One is a scientific one and one is not a scientific one. The scientific one is, could you tell us more about the radio observations that led to the very fine, the innermost point in the mass profile? And my non-scientific question, Reinhard, is you've also had a fantastic career in galaxy evolution. And I was just wondering, what fraction of your time did you spend on symphony, etc., on the black hole in the Milky Way, and what fraction did you spend on galaxy evolution?
Gary, that's a very good question. Let's see. First off, let me, the innermost point which I showed in terms of the mass distribution comes from the motion of these flares. And indeed, I should say, if we would have a number of these flares coming in the next years, I'm fairly confident that we might even get the spin from that. And in particular, also a test of the Peterson effect, because it's not at all clear that in a thin accretion environment like the galactic center, the accretion disk is perpendicular to the spin of the black hole. Okay, that's number one. Number two, which I didn't mention, is we have learned from the gravity measurements in this innermost zone that there's a very strong magnetic field. So in contrast to most everyone's assumptions, Brigitte, yeah.
Brigitte.
In contrast to most everyone's assumptions, the gas pressure does not dominate. And that's in fact the same the radio astronomy group finds in M87. So that's a bit of a game changer, that apparently the magnetic energy of the black hole is the dominant one in the central region. Okay, your second part of the question. Fortunately, many of the instrumentation we have developed, like for instance, Symphony, like for instance, NACO, and even gravity, can be applied to this other branch of our research. In my group, I would say 2/3 and more are actually working on distant galaxies. I myself tend to, jump from one to the other. Now, as I'm getting older, I cannot do it simultaneously. I spend a month or 2 or 3 on the one side, and then I go back to the other side. It's fantastic. I mean, keeps you alive and lively if you do that, because it's so exciting.
Okay, thank you very much. Good luck for your perspectives, which are very exciting.
Thank you. I think Felix, you have a question from Buenos Aires.
Yes. What is your opinion about the possibility of clear evidences of jets from Sagittarius A star?
Yeah, good question. Well, I think let's wait until the EHT people come up with the image. If you ask Heino Falke as an example, he would tell you that the symmetry of the 3 millimeter image already excludes there to be any strong jets. Okay. Now, what does that mean? Well, surely it means there's not much particle streams going out, which would be somewhat consistent with the low density of gas, which I mentioned, okay? The other thing it might indicate is that in contrast to M87, that the spin of the black hole is low. And that's likely because the situation in the galactic center, we know that, is that the accretion lately, let's say over the last millions of years, has been dominated by these stellar winds, which are orbited in various different directions, not the plane of the Milky Way by any means. And so in such a situation, you would get, a bit of a kick on Mondays from one side, and on Fridays, the kick comes from the other side. So I personally think when we can do that, we'll find that this is closer to a Schwarzschild hole than a Kerr hole.
Yes, there were some people claiming that the spin in Sagittarius A star is relatively low compared with the spins in the more powerful regions.
Yeah.
Thank you very much.
Thank you. Are there any other questions? Please raise your hand. Or there seems to be no more questions.
Brigitte, you can go ahead and write to me afterwards, and I'm happy to respond to you in email.
But that's very kind. Thank you, Reinhard. So please do so. Any word from Francois or? So that free. So Marta has another question.
I mean, if I can ask another one, it's about the Higgs mechanism. So you said that the stars closest to the black hole are probably produced by the Higgs mechanism. So I was just wondering, how far away could the binaries be produced to migrate and have the binary disrupted, and still these stars be young enough to be as we observe them? And I'm not sure if this.
Yeah, well, okay, this depends very much on the reservoir. And you may recall Tal Alexander's work on that, which indicates that if you look at the closer environment, like say the central parsec, while you're closer, the amount of stars which are available to you as a reservoir is relatively small. Whilst if you go parsecs away, like 10 parsecs away, there you have these big clouds. And so just look at the formula, you will find that the lost Cohen rates so strongly depend on the reservoir mass that you would expect them to come from a large distance. Now it's interesting, we are now through these measurements, of course, as you might imagine, are getting more and more and better measurements of the ellipticity distribution of the innermost stars. And it's very, very clear now that the ellipticity distribution is more elliptical than a thermal distribution. So that is indeed what you would expect in hills. Now, there have been papers written that you could generate the same thing if you come from a disk nearby, so the disk stars, and then bring them inward by perturbations if you have an intermediate mass black hole. But if you believe the evidence, which I showed, that we can now exclude an intermediate mass black hole, I would personally say any kind of an in-plane, inside migration process just takes too long, and certainly wouldn't produce such highly elliptical orbits.
Thank you.
So I don't see any further hands raised, and so perhaps Felix, you still have Edith has a question.
Well, maybe it's a very interesting question. Thanks very much for your talk, Reinhard. My question was, can you estimate the mass accretion rate of the black hole?
Yeah, so the best measurement we have on that is the Faraday rotation of the millimeter source or sub-millimeter source. And that's been measured fairly accurately. And that you can turn into a density. And that then you can turn into an accretion rate. And that turns out to be about a few by 10 to minus 9 solar masses per year. Maybe 10 to minus 8, but not more. Now that would be on scales of the millimeter source. So 10 times the event horizon scale, roughly speaking. Now we have other pieces of evidence, which is interesting. The most exciting I find is the fact that the little object G2, I don't know whether you call that, which made its way through the center on a highly elliptical orbit and then went back out, in which we think is a gas cloud. It got tidally stretched by an enormous factor, maybe with a central star, but that the main point is that the gas is totally affected by the tidal forces from the black hole. Now that star or that gas cloud plus star or gas cloud is slowing down. From this, we can estimate the density of the gas in the vicinity of about 1,000 to 2,000 Schwarzschild radii, and that is consistent with that low accretion rate from the Faraday rotation.
Thanks. And this is consistent with the frequency of the flares that you observe?
Yeah, the flares don't require much material. You know, one of these flares are not accretion events. Okay, they are acceleration events. So what you need to do is to accelerate the electrons in this innermost region from an average relativistic gamma of about 10 to 100. That would be the equipartition number. So that's about 100 million degrees to about gamma of 1,000. And the X-ray flares, which sometimes accompany the infrared flares, would require gammas of 1 million or 100,000. So so this is not an accretion event. It's just the fact that a few percent of the electrons in the innermost region, probably through magnetic reconnection, are accelerated by a large factor.
Okay, thank you. It's very fascinating.
I do agree. Perhaps room for a last question here. I think, Michel, you have your hand raised.
Yes. Hello, Reinhard.
Hello, Michelle.
Yes, you mentioned plans for improved instruments in gravity on one hand, but also a Mikado type on the ELT. I was wondering, what do you expect eventually to do better with the ELT than with the VLT, as the angular resolution of the ELT is not matching by far the one you get with an interferometer?
Yeah, you are absolutely right. Good question. I tried to address that already, but let me recapture what I wanted to say. So absolutely, the resolution is not competitive. In fact, let me comment right there. This is a very important limitation for 8-meter class astrometry. The density of the central region is so high that in the central 0.3 arc seconds, the probability to be confused in the imagery with an 8-meter class telescope with another fainter star is very high, and therefore much of the ultimate performance, shall we say, of the 10-meter class astrometry is limited by confusion and not by signal noise ratio or something like this. But, and here comes the trick, sensitivity. Okay, so unfortunately, the many mirrors, 25 mirrors, okay, 25 mirrors bouncing, okay, and we have a effective quantum efficiency with this gravity of about 1%. I'm ashamed. Okay, I'm ashamed. It's not, can't change it. In Mikado, of course, we would have hopefully a quantum efficiency of, say, 25%, 30%. Combine that with a 39-meter telescope and good adaptive optics. I mean, your orders of magnitude more sensitive. Thereby, you can then go to high spectral resolution. And a number of the innermost stars are not B stars, but actually G stars. And of course, G stars, as we well know, have many lines. So then you can push the current spectral resolution limit is a few kilometers per second. But we are fairly sure with G stars, we could push that to meters per second. With meters per second, you can imagine you can do basically Doppler effect GR tests like a pulsar.
Okay, thank you very much.
So I think it's we will probably end here, and I don't see any hand raised. But so again, Reinhard, many thanks for this wonderful presentation of your journey and all these beautiful results, and also for sketching the future that looks so bright, so interesting. And again, I want to thank you for offering to answer any questions that wouldn't have been asked now, that if people are interested can be sent to Reinhard via email. So again, it's a pity that you weren't there present physically, but it was a very nice colloquium and with wonderful results and many thanks.
Well, thank you, all colleagues and friends in Paris. Good, okay. Good to see you in 2 dimensions.
Bye.
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 Take care, Reinhard.